Okay, this is the pedal of my EUC. The pedal is tall because it is designed for off-road riding, but I use it for commute. So I want to lower it down because when I ride in stop and go traffic, I need to hop up onto the pedals and it requires a lot of energy to jump onto the pedal. I'm planning to lower it down for 25 millimeters. So the pedal is held to the bracket by using the pin. This is 8 millimeter pins, and the pedal is collapsible. When it's fully opened, it's going to compress against this compression face. To push out the pin, 8 millimeters, 8.3. It's loose fitting. Okay, this is how it works. So when the rider put the foot on the pedal is going to pull away from the pin like this, and it's going to compress against this face here. So this is a simple lever mechanism, and the space between the center of the hole to the compression face is about 15 millimeters. And the distance between the pin to the center of the pedal is 6 centimeters. This 8 millimeter pins has a double shear. It has two shear planes, 1 and 2. For the 8 millimeters pin made from steel, it can resist up to 15 kilonewtons or somewhere around 1.5 tons of the shear load. This is the braking load. 60 millimeter from the rotation point. So this is just a simple beam lever. So when I apply 80 kilogram force here, which is the weight of the rider, the distance from here to here is 15 millimeter. 60 divided by 15, that would be 4. So 80 kilogram will translate into 320 kilograms on this contact face. So this pin is 8 millimeter, so it can carry shear force 1500 kilograms. It's going to be a reaction at the same amount. This will be the load that will be applied in a model for stress analysis. So the rider weight should be 1500 divided by 4, which is equal to 375 kilograms. But for the mechanical part like this is involve the safety of the rider. Usually we use safety factor equal to 2. The safety load for the rider on one pedal would be 375 kilograms divided by 2, which is around 180 kilograms. This is a static load, not dynamic. So if it's dynamic load, like when the rider is jumping, it's going to be a lot less than 180 kilograms. So this bracket is very wide because when the rider step onto the front part of the pedal, it's going to twist. So the wider is also the better to resist the rotation. Okay, for the new design, I'm going to lower the center of the hole here down 25 millimeters. I think the original part was made by using extrusion. They extrude these profiles. I can see the tool mark. They use the circular saw to cut it. After they cut it, I think this part is made by CNC milling. They mill this part as well because I can see the 2 bits marking. This cutout here is from the extrusion, and they have to make a hole here for the grab screw. They need to tap the threads here. But the new part that I'm going to make is going to be milled from a solid piece of aluminum, which is it could be very expensive. I have no idea how much it will cost, but until then, let's start with the 3D scanning. RapidDirect offer to sponsor the CNC part in this video. They also have other service like injection molding, sheet metal, 3D printing, extrusion, die casting. So if you want to make a prototype like this one, you can try using that service. I put the link in the description. To make a 3D scan of the part that require high precision like this, I recommend that you should calibrate your 3D scanner. The machining cost is expensive. It's not a 3D printing, so you need to be sure that you have the most accurate output. I will scan this part in 4 orientation, 1, 2, 3, and 4. Before you start, you need to do a global marker. Okay, then I'm going to scan the markers. There are 136 marker here. I remember it. I'm going to use 0.15 mm for the resolution and scan in the parallel lines. Okay, now you can see from the preview screen, it's not capturing this kind of black texture. And if I increase the laser brightness, it still cannot detect. See here, try to scan it. It can capture the black turntable, but not the part. See here. Okay, here's the Raptor X. I'm gonna use 7 line. So now you see the difference. The Raptors can capture this kind of black surface, but when I lean it to the side, it cannot capture. See here, it cannot capture the side, but it can capture the top. Some certain roughness, it can reflect all the light from the scanner. In this case, you need to use the spray. Okay, let's start scan. So you can see that now the S1 can capture the surface much easier and quicker. So it has 90 frames per second. I'm going to switch to a single line. 1, 2, 3. Create plane check mark. This is the other side. I can scan quicker. It's a real-time speed. I want to scan the sidewall of the hole as deep as possible because you can locate the center of the hole easier if you have a sidewall scan. And check mark. I'm going to flip this. Okay, like this. Okay, next I'm going to align them together. Use manual alignment. I'm going to pick the scan 4 in the fixed window and scan 1 in the floating window. Okay, let's align them. Okay, now 1 and 4 is aligned together. Next I'm going to align 2. 1, 3. Okay, now we have the last one. Okay, full scan aligned. Next I'm going to mesh it together. 4 million would be enough. Okay, this is the mesh result from the full scan. Can't even see the threads here. Okay, next I'm going to export this as a point cloud. I'm going to drag and drop the files here. Click on apply. So I have about 1 million point clouds. I'm going to align this mounting face here to the XY plane. Click here, click on 3 points. So now it's aligned to the XY plane. Next I'm going to align it to the x-axis, zoom in, move, and I'm going to use my mouse to rotate it and use the edge of the monitor as a reference. I have a 4K monitor, so I can clearly see the alignment like this. I'm going to do a recheck again when I import to the Autodesk Inventor. Next, I'm going to move this registration, move bounding box to origin. So now the center of the box here should be at the 0 point. So now it's ready for exporting to the Autodesk Inventor. Okay, this is Autodesk Inventor. Okay, first I'm going to check the alignment by creating a sketch on the XY plane like this, and I'm going to draw a line, and this line will be a horizontal line and this line will be a vertical line. I'm going to move it here. Maybe you can see this if you use a 4K monitor. If the wall line from the scanner is very thin like this, you can easily see the alignment of the point cloud. Now it's aligned to the horizontal plane. Let me check the 90 degrees angle. It looks okay for the 90 degrees. So this part is rotational aligned. Next, I'm going to check the center line because I'm going to draw only 1/2 of this part, and I'm going to use a mirror function to mirror it. So I'm going to draw a straight line from this point, and next I'm going to draw the line at the center. This is the misalignment from the center, so it's only 4 microns. My point cloud is exactly in the center of the origin. I'm going to crop a thin section of the point cloud here, and I'm going to use this cross section for tracing. Okay, this is the first sketch that I'm going to make. I will trace the external profiles that the original designer used for doing aluminum extrusion, and then I will make an extrusion cut later after I make this profile. For the part that's going to be machined with a CNC, you need to trace with a higher precision, so each line has to be matched perfectly onto the point cloud. If your 3D scan wall thickness is very thin, then you can trace with higher precision, okay, like this. And if you want to draw the center of the circle, I will use 3 line arcs to find the center first. So this is the center of the circle, and then I'm going to use a circle command. So this is how I'm finding the position of the hole in the sketch. I will extrude the profiles 50.15 millimeter. Okay, this will be the second sketch that you for cutting the internal profiles. Okay, and then I extrude cut it. This will be the hole cutting. Okay, I'm going to cut the pocket here. Okay, I draw a sketch for the hole, 6.3 millimeter diameter, and do extrude cut. Okay, I'm cutting the pocket, make a fillet here, and then I mirror the extrusion that I made to the other side using this XY plane. Next, I create a plane here at this location, and then I create this sketch here for cutting. Okay, and then I cut it. Okay, this is how it looks. I'll create another sketch here and extrude it. I use a chamfer command to chamfer this 2 corners and fillet this 2 corners. Next, I draw a sketch to make a hole cutting and use extrude cut to cut it. Make another sketch here and extrude cut for the counter bore of the hole. Okay, and I use thread command. For the female thread, if it's M5, the diameter of the hole is 5 millimeter, but the male thread will be smaller than 5. And for the Autodesk Inventor, it's not going to actually draw a helical thread as a solid model. It's just a symbolic thread. So if I export this as a stepwise, it's not going to show the thread in the model. After I done this, I will have to do 2D drawings so that the operator will know this hole include the thread, M5 thread. So it's necessary to also provide the operator with the 2D shop drawing. Okay, I make another sketch here. It's a cutout for the grab screw. Then I make an extrusion to here, and then I make a hole with a thread. This is a female thread, M8. Then I add a fillet here and here, 1mm. Add another fillet in this corner. Make a small fillet extrusion here. This is the original part, reverse. It takes less than 15 minutes. Okay, let's put this into the simulation. Let's see if it can hold up 8mm pin here at 1.5 tons. Okay, stress analysis. Assign the materials 6061 aluminum. Next, I'm going to create a frictionless support here and fix support on the edge of the hole. Next, I'm going to apply the force along this axis, 15 kilonewtons, 1.5 tons. Also apply the load here, 15000 Newton. Okay, next let's try to simulate this. Check the 1 missing stress, 265, 6061. Aluminum alloy has ultimate tensile stress 280 megapascal. So this one is all blue. Only concentrate on the mounting holes. I think the original part has a washer to distribute the load, so it's not going to be like this in the real part. This bracket will not break even the pin snap off, so it's stronger than the pins. This part is safe to use. It's well designed. A little bit of the over design. When it's too strong for the strength, it doesn't mean that the designer is wrong. They do this to control the stiffness of the part, so that when the rider is riding, it will feel secure when they step on the pedal. Let's check the movement. Okay, the movement is only 97 microns. Okay, it's hard work. Okay, now I'm making the lower version. I copy the original part, change the file name, and then I clone this sketch and move it down 25mm from this point. First step, I cut the whole part here. I only leave the bracket area here. After I cut it, I create a new extrusion using the sketch that I lower it down 25mm. So this will be the new profiles. So I make the extrusion cut here. It has to be accessible by the screwdriver. Then I make a fillet here along the edges. Then I make a hollow cutout. This will be the hollow cutout. And then I add some fillet here. Then I make a cutout for the grab screws. Make a M8 hole with the threads. Add some fillet here. Okay, that's it. This will be the lower version, 25mm. Because when I ride in the traffic, I have to start and stop many times. So if I get a lower pedal, so it'd be more comfortable for me to step up and down the EUC. So when comparing with the original part, the transparent one, so it's quite a lot lower. Okay, let's simulate for the stress. I apply the same load. There's a bit more stress here on the mounting hole, which is not true because it's going to be covered with the washer to distribute the load. I can see some stress concentration, but it's 162 megapascal, which is still safe for the 6061 aluminum. So this part is still safe even though it's lower. The original part is much stronger, but when you lower it, it changes the direction of the load. So it's not as strong as the original part, but it's still safe. The 8mm pin here will fail before the bracket, so it's safe to use. Okay, let's compare the weight. Original part weight 193 grams, and the new one weight 155 grams. So it's a little bit lighter than the original part. The cord is shorter. Before I can send this to the RapidDirect, I need to make a a production drawing, a shop drawing. Okay, to make 3D drawings, I click here, standard IDW, base wheel, custom view orientation. I'm going to make a 3D view of this. Let's say 1, 2, 2, about this small. Okay. And next I'm going to project the wheel. Make a cross section. I'm going to pull it right here. So it's also display all the threads here, which is necessary to identify. Okay, let me do another cross section here. Let's start to do a dimension. So I'm going to identify this angle because it's very important. Okay, it should be good enough. I'm going to click on save. I'm not going to specify all the dimension because they have the step files. Okay, this is a RapidDirect website. So I never tried to use this service before. So I'm going to drop the step files that I draw here. Okay, so I think I uploaded it twice. I'm going to delete this one. Click on configure. Okay, so the part is here. That's nice. Let's try to view it. So the part that you draw will be uploaded here. Let's check the dimension. This to this. Okay, 50.17. Yes, that's correct. I measure it with the vernier caliper. So get this number. Let's cross section. That's nice. You see that it doesn't show the threads. The threads that I draw here in the address Inventor is not showing as a thread. It's showing as a whole. So you need to upload the shop drawings so that they know that the 2 holes here is the thread. I'm going to choose the finish. They have sandblasting, number 150. I think I'm going to try black plain coating. Quantity is 2 because it's both sides. I'm going to click on apply, right? Okay, next I'm going to upload 2D drawings. Okay, 2D drawing is upload. Cosmetic part. What does that mean? Cosmetic part. Part cannot have cosmetic defects on primary side. I don't care, it's just a bracket. Tightest tolerance. Oh, they have a ISO standard. What's that? When I was in the engineering school 26 years ago, it don't have this. Thread and tapered holes. Yes, they have a standard threads. I have already provided 2D drawings. Because a CNC machine, it's not going to create a thread from 3D models. So it's going to use a G-code to generate a thread. Standard thread. The operator needs the 2D drawings, shop drawings. Insert, no insert. Part marking, no, I don't need any marking. So you can add the laser marking like the brand name. Inspection report, I don't need that because I have a 3D scanner. After they produce it, I'm going to inspect using the 3D scanner. Remark, I don't have any remark. Shipping, I'm going to go with the DHL. So I'm going to request for menu quotation. Okay, so I guess I will have to wait. It said right here, our engineer team will review your part and provide quote. So I wait for the email, I think, and see if I can get the price by tomorrow. So that's the end of the video. Until I get the parts and test fitting. Thanks you guys for watching. I'll see you in the next video.